A physics problem with an exact answer. Take an elephant to the top of Toronto's CN Tower and throw it off. What happens? The tower is 553 meters tall, but the top is antenna nobody can stand on. The highest place you can stand outside is Edgewalk, on the roof of the main pod, 356 meters up. Our elephant is an adult male African bush elephant, 6,000 kilograms, 3.2 meters at the shoulder. Start with the simplest model, no air at all. Gravity pulls everything down at 9.81 meters per second squared. Energy is conserved. Potential energy, mass times gravity times height, becomes kinetic energy, 1/2 mass times speed squared. Mass sits on both sides, so it cancels. That is why a feather and a hammer fall together on the moon. Solve for speed, the square root of 2gh. That is 83.5 meters per second in 8.5 seconds. But air is not nothing. A cubic meter weighs 1.25 kilograms, and the elephant has to shove it aside. The force air pushes back with is called drag. 1/2 times air density times the shape factor times frontal area times speed squared. Speed squared is what matters. Go twice as fast, and the air pushes back 4 times as hot. For our elephant, density 1.225, shape factor 1 for a blunt body, and a belly-down silhouette near 10 square meters. Now watch, weight never changes, but drag grows with speed. Sooner or later, the two must become equal. When they do, the total force is 0. The elephant stops speeding up and falls at a constant speed. That is terminal velocity. Set drag equal to weight and solve the square root of twice the weight over density, shape factor, and area. 98 meters per second. Look hard at that. It is higher than the 83.5 we got with no air. So the elephant never reaches terminal velocity. Getting within 1% takes nearly 2 kilometers of falling. The tower is 1/5 of that. So we solve the real equation instead. Gravity pulling down, drag pushing back, all the way down. The exact answer is terminal velocity times the square root of 1 minus e to the minus 2gh over v terminal squared. Put the numbers in. 70.5 meters per second, 254 kilometers an hour, after 9 seconds. So air cost it 16% of its speed, and the throw, 5 meters per second sideways, carries it 40 meters out. Energy decides the landing. 1/2 times 6,000 kilograms times 70.5 squared is 14.9 megajoules. That is about 3.5 kilograms of TNT arriving all at once in one place. 6 more megajoules never arrived. They went into warming the air. 29% of the fall heated Toronto. Now, the number that decides everything. How far the elephant travels while stopping. Its own body crushes by roughly 1 meter. Deceleration is speed squared over twice that distance. 2,480 meters per second squared. 253 g. Force is mass times acceleration. Just under 15 meganewtons, or 253 times the elephant's own weight. A skeleton carries 2 to 4 times body weight. The most a human has survived is 46 grams. Doubling our area guess changes little. Which raises the better question. Why does a mouse dropped down a mine shaft, land, shake itself, and walk away? Terminal velocity goes as mass over frontal area. Mass grows with a cube of size. Area with a square. Bigger things fall faster. A mouse tops out at 10 meters per second, a person at 43, our elephant at 98. Per kilogram, it lands with 47 times the mouse's energy. So step back and look at what this whole answer rests on. It is one line. Terminal velocity is 4 times the square root of mass over frontal area, in kilograms and square meters. Try it on yourself. 80 kilograms over 7/10 of a square meter gives 43 meters per second. Skydivers measure about 50.